the dopant distribution is very sensitive to the segregation coefficient K naught. Okay, so in Chakrowski, he found that the dopant concentration in a solid is going to be initial concentration and the K naught segregation coefficient and the fraction of solidified, and exponentially is proportional to the K naught in this fashion. Okay. So in a boron, the K naught value is about 0.8, and the phosphorus and arsenic, the N-type dopants, is about 0.3. So we're supposed to have relatively uniform distribution of the dopant in the ingot of a single crystal of silicon in boron case compared to the N-type dopants. Okay, that we have been discussed last time. And today we're going to discuss about another single crystal growing technique, which is called the float zone technique. Okay. In this float zone technique, it has been shown in the note that we have a float zone here, the melting zone and length L, and the single crystal seed supposed to be located at the bottom, and on the top we have a rod-shaped polycrystal of silicon. Okay, that is a solid, and this molten zone is going to be scanned over from the bottom to the top of the polycrystal, and then melting and freezing is to subsequently happen. So key variable is going to be zone length, of course, charge length, the total length of the polycrystal silicon rod, and initial solid distribution, vapor pressure, mixing condition, zone traveling rate. And among these, we are mainly concerned about the solid distribution, the relationship with the solute dopant distribution in the single crystals of silicon, and we want to see how sensitive the dopant distribution is with respect to the segregation coefficient K naught in the float zone technique. In that analysis, what we are going to do is we are going to, let's see, we have single crystal here, and this is the polycrystal rod to be crystallized, and this is the part, the solidified and the liquid zone or molten zone. The length is going to be L here, and here is a polycrystal. Again, it's a solid, and this molten zone is going to move towards this direction. So let's suppose it has moved to the dx. Okay, it moves to the dx like this. Okay, then this part, this much is going to be incorporated in the liquid, and this part is going to be solidified, newly solidified. Okay, so what we try to calculate here is that the dopant change in the molten zone with moving the molten zone length L dx. Okay? So this is a single crystal. And here this part is a polycrystal. Okay? And by moving dx, the number of dopant atoms incorporated into the molten zone is this much. Okay, A is the area and dx is the moving distance. Okay, so basically this A dx is the volume that has been changed, that has been incorporated into the liquid. Okay, and then K naught is the segregation coefficient, and I over L A, and again the volume. It's going to be the dopant atoms incorporated into the solid. So the total change of the amount of dopant atoms in the molten zone is going to be this much. Okay, with the moving dx of the molten zone. So this is the change in the number of dopant in the molten zone. So you should remember this, that the I is the number of dopant and the molten zone. Okay. Then we have to solve this partial differential equation, the first order ordinary partial differential equation, and that is a long time ago you guys have learned this. Okay, let me just do this here again, and I dx is equal to di. I just change this equation, and then I arrange that. It's going to be K naught over Li equal to NMA. Okay, and we are supposed to have a general solution of this. You have to remember the mathematics that you have been learned in a long time ago. Okay, you set I equal to A to the Rx, and then R is going to be minus K naught over L. Okay, and the particular solution you set I is for particular solution I is equal to some constant value, and you put it there, and this constant value end up with NMAL over K naught. Okay, so the we can So we can set the solution of this, some constant K naught over Lx plus NM K naught AL, things like this, okay? We apply the boundary conditions, which is at x equal to 0, at the very beginning of the solidification, single crystal growing. The dopant amount in the molten zone is, of course, it's going to be like this, okay? So that we apply this boundary condition to the equation, and Nm over K naught AL. So we can set this constant like Nm AL 1 minus 1 over K naught. So the solution is going to be I is equal to N MAL over K naught minus 1 minus e to the minus K naught over Lx plus 1. Okay. So this is a little bit different from what we have in the Czechoslovsky case. Now, the key variable here is K naught over L. L is the molten zone length, okay? So in a flow zone technique, we have important variable, of course the K naught, and then L, the molten zone length as well. Okay, so you apply this equation, and this is a computer simulation of the dopant. No, this is the Czechoslovsky one. This is the flow zone technique for dopant distribution, and the numbers you can see in this figure is the number of path of the molten zone. In a flow zone technique, you can go up, you can move the molten zone to the up direction, and then go down and up and down. You can repeat the scan of the molten zone, and this is the resulting the dopant distribution along the length of the polycrystal rod. Okay, actually it's a single crystal, but it just shows the dopant distribution. After one path, you have this much difference along the length of the polycrystalline rod, single crystal rod, as a dopant distribution, and then you move to the opposite direction, and that is a number 2. You can see the number 2 there. Number 2. Okay, and then number 3, number 4, number 5, number 6, and the opposite directions again, and then you can see at the number 10, almost a flat distribution of the dopants. Okay. So obviously you can see that compared to the Czechoslovsky flow zone technique, it is not that advantageous to make a big wafers. But you just repeat the scan, then you have a flat distribution of the dopants along the length of the single crystal in the flow zone technique, no matter what the K naught value is. Okay, that is the advantage. But the real advantage of the flow zone technique can be seen from this comparisons. This is a comparison of Czechoslovsky and flow zone crystal growing method. And here the large crystal Czechoslovsky is possible, but the flow zone is difficult. If you want to make a big wafers, then the heating zone should be big, should have a large diameter. And then in that case, you have a rod here, and then the heating zone is, it forms like this, okay? It's surrounding the rod like this, so that towards the radius, you cannot have the uniform temperature, okay? Of course, from the outside towards the inside, you have a different temperature, so that you should have a temperature gradient. And if you have a larger crystals, then this temperature difference from the outmost and the core, it should be big, so that it is very hard to make a big wafers, big single crystals with the flow-joint technique. So so far, we are making 6-inch and most with the flow-joint technique. While in the Czechoslovakia we have 300 millimeters, which is about 8-inch. Okay, so you're pretty much different. Coast Czechoslovakia is much cheaper, and this location there is a defect density, you should say. In Czechoslovakia, it's relatively lower than the flow joint. So far, nothing advantageous of the flow joint technique, nothing merit we can see comparing to the Czechoslovakia, but the resistivity, that is Czechoslovakia, we can have a maximum 100 ohm centimeter, but in the flow joint, we can have 2,000 ohm maximum, which means we have a high purity single crystal silicon wafers with the flow joint comparing to the Czechoslovakia. Okay? That's why we have a high resistivity. High resistivity means we have a more pure single crystal. And about the same radial resistivity, there is a radial distribution in horizontal directions. And now the most important difference is the oxygen content. In a Czechoslovakia, even if it is a single crystal, we have interstitial oxygens, which does not disturb the crystal structure, but we do have impurities like interstitial oxygens, and in Czechoslovakia it is a 10 to 16 to 10 to 18th, while in a flow joint technique we almost none. And this oxygen, interstitial oxygen, comes from the vessels of the Czechoslovakia. As we discussed earlier, we have a very large silica vessels to contain the molten silicon, okay? Molten silicon at the temperature almost 1420 degrees centigrade to melt the silicon, right? And then we, in a crystal growing, we have a single crystal silicon, tiny single crystal silicon seed, and that is rotating along this horizontal axis to make a uniform distribution of the temperature, dopants, whatsoever. Okay, has a uniform crystal growing along the radial directions. We have to rotate this, and one of the drawback of this rotation is the incorporation of interstitial oxygen into the molten silicon coming from these silica vessel. Okay, and then that interstitial oxygen is going to be incorporated into the solid silicon during the freezing process. And but this is not trivial amount. As you can see, it's a 10 to the 16th or 10 to the 18th. The absolute number is big, but if you think the single crystal silicon, the atomic density is about 5 times the 10 to the 22 atoms per cube, and compared to that, that is just less than ppm order. But electrically, it affects the electrical properties of a single crystal silicon considerably. So it is not a trivial question at all. So if you want to have a really, really good single crystal, you have to go for the float zone technique rather than the Czochralski. But in most DRAM industrial process, you really don't have to go for that high quality silicon. We just use the Czochralski silicon wafers, and we have means to get rid of this oxygen content in the Czochralski. That is called the gathering. Okay. Gathering. That is, when you see the silicon wafer, you have a thickness of the silicon wafer about 600 microns in thickness. Okay, the thickness of this silicon wafer is typically 600 microns of the 8-inch diameter wafers. Of course, if you make a smaller diameter of the wafer, you can decrease the thickness of this like a 200 microns for the 6-inch. Basically, why you want to maintain this thickness of the wafer is to prevent the warpage during the heat process. If it's too thin and it's wide, then during the heat treatment, it just twists, we call the warpage. So in order to prevent that, we have to maintain certain thickness of the silicon wafer, and that is the 600 microns. Now, if you build the MOS transistors on top of this, the junction depth typically, this is source, drain, and gate. This junction depth is typically about 1,000 angstrom, which means among this 600 thickness of the wafer, we just use at most top 1 micron in depth. We just build the transistors just using the top 1 micron thick surface of the 600 silicon wafer. And the rest, 599 micron, we do not use this as a single crystal. We just use this as a substrate. Okay? So if you want to have a perfect single crystal without any defect, all you need is just 1 micron on the top should be defect-free. And you don't care about the 599 microns of the silicon wafer. So people try to use the Czochralski wafer, and then it does have interstitial oxygens all over, but during the gathering process, you're going to create about the 10 micron, we call that the denuded zone. Means interstitial oxygen free zone. Now how do you get it? You use the heat cycles you heating up and cool down and heating up and cool down, then this surface has a different potential with respect to the inside of this wafer. So that potential difference drives the oxygen, surface oxygen into the bark. Okay, so that we can create some oxygen-free denuded zone from the top. Or we can damage on the back side of the wafer by the sandpaper, and we're going to discuss about the ion implantation later, but using the ion implantation of argons and so forth, so that we damage it on the back side of the wafer and then put it in the heat cycle, then the top oxygens or defects, any other contaminants like iron and things like that, okay, those kind of impurities will be diffused towards the high potential area, which is on the opposite side of the wafer, so that we can create the denuded zone. So we have many techniques to get just one 10 micron oxygen interstitial oxygen free zones, okay, so that it is very comfortable to use Czochralski silica wafers instead of high quality, expensive float zone wafers. Okay, that is a very common technique. Okay, that's pretty much about the single crystal growing. And if you guys don't have a question, then we are going to move to the next chapter, diffusion process. All right? Okay. Diffusion. In this VLSI process, the diffusion process is needed to mix the dopant atoms into single crystal silicon. Okay. So for this, we use the diffusion process. Diffusion process is a very old technique. Okay, and we have like this is MOS structure, and then we can have PMOS, P-type MOS or N-type MOS. Okay. Then P-type MOS means the source and drains. We have heavily doped P+ regions for the source and drains like this, and then MOS is M+ like this, so that electron is basically used for the operation of this transistors, and holes for the PMOS. And MOS is preferred because, as you may know, the electron mobility is 4 times higher than that of holes, right? So we have a faster response time and everything, faster speed, so that the MOS is preferred than the PMOS. Now for this, we should have a N-type silicon wafer to make a PMOS here, and then we need a P-type silicon for the MOS to make a junctions here. we do have to have junctions here, like this, okay? So that the 600 micron silicon wafer has to be doped. And for the diffusion process, we just can have only 1,000 angstrom diffusion of the dopant atoms. So in the semiconductor, when you talk about the diffusion, we are talking about the 1,000 angstrom diffusion length as a diffusion length, right? This 600 microns, we cannot have this much diffused length in the solid state, okay? Just for 1,000 angstrom, we have a very elevated temperatures, like above 1,000 degrees centigrade, for typically 1 or 2 hours to make a diffusion like this. As you see, the diffusion coefficient has a unit of centimeter square per sec. Okay, so the diffusion length, as a rule of thumb, you have to multiply with the time and the diffusion coefficient, and the square root of that is the length. So let's see, at 1,000 degrees centigrade, this is a pretty high temperature, and the diffusion coefficient is typically 10 to the minus 9 or something in a solid state, centimeter square per sec, okay? So if you, let's suppose your 1 hour is 3,600 seconds, okay? So 4 times 10 to the 3 second is about 1 hour. And you multiply with the 10 to minus 9, and you end up with the 10 to minus 6, okay? And then square root of that is the length, so it's 10 to minus 3 centimeters as a diffusion length. Which means if you make a diffusion at 1,000 degrees centigrade for an hour, the length that the dopants can travel along the depth, diffusion length, is 10 to minus 3 centimeters. What is the 10 to minus 3 centimeters? That is the 10 microns. Only 10 micron can be diffused into the substrate, okay? So the dimensions we are talking about, the scales we are talking about, is this, something like that. And the diffusion process in the semiconductor can be distinguished by 2 steps. One is the pre-deposition, and the other is the drive-in, okay? The diffusion process